Hello, good afternoon, everybody, and welcome at this Flanders Make Tech at Lunch webinar. My name is Jurgen van Emps. I am a professor at the Flanders Make at VUB Core Lab BVOT, and today I'd like to show you how photonics can be a key digital technology for innovation in the 21st century. Before we get started, a few housekeeping items. So the cameras and microphones on your side are muted by default. If you have any questions during my presentation, don't hesitate to put them in the Q&A chat box, and I will answer them at the end of the session. And finally, no need to make a recording of this session because it will actually be shared at the end of the event, so you can use the recording later on. Okay, so the European Commission has identified 8 key digital technologies for innovation and digitization, and photonics is actually one of those 8 technologies. And what is photonics? Well, photonics is the science and technology that innovates with the unique properties of light. So everything that has to do with light generation, light manipulation, and light detection for the benefit of mankind, basically. Now, so as one of these 8 key digital technologies, it is important to see that although the term might not sound familiar, photonics is a key part of many aspects in our daily lives and is used in many different application domains. For example, optical telecom, while the backbone of our internet as we know it today is basically made up of optical fibers that can transport data from point A to point B at very high speeds at very high bit rates. Other examples, photovoltaics, for example. So in the green deal, in green energy generation, LED lighting with LED light sources that are completely replacing more traditional light sources because they are 5,000 times more efficient, and they have a lifetime that is 5,000 times larger as well. Display technology is another example. Lasers can also be used in manufacturing for welding or for cutting or even for 3D printing or subtractive machining. Also in the health industry, optics are used in the medical optics domain. Machine vision is another example where imaging is being used to control products that are being manufactured. So in general, optical components play a huge role in our daily lives, and I will illustrate that with other examples as my presentation goes on. Some numbers on the economical side of things. Well, actually, if you look at the global market share of photonics, well, the EU is actually has the second largest share worldwide behind China, which is #1 at the moment. But the EU share is about 16%, or in numbers that is 102.5 billion euros. So photonics is a quite important domain for the EU. So, for example, in production technologies, measurement and automation, the EU market share is really large. The compound annual growth rate reaches a number even of 7%, which is very high. If you look at some of the workforce in Europe, more than 5,000 SMEs in the EU are somehow related to photonics, and that means that there are about 380,000 direct people employed in the EU with this photonics technology. So overall, I could say that photonics is a win-win-win-win scenario because it can contribute to sustainable development in the Green Deal, so helping to save energy consumption and to get to a greener environment. So as such, it also has a big societal impact. For example, you could think of using lasers in medicine applications or optical detection techniques in early diagnosis of diseases. But also, of course, it plays a major role in innovation and digital transformation in general, and can contribute to the economic competitiveness and technological sovereignty, as I just mentioned with some of these numbers that I presented. So overall, we could say that photonics is a long-term enabler for innovation and the creation of revenues and new jobs, and this in all industry sectors, basically. So a few sectors are mentioned here on this slide. So in the middle, you have the photonics core technologies here, And then surrounding those photonics core technologies, you have all the different application domains ranging from health, so with, as I mentioned, endoscopy, laser-based surgery, and so on. Agri-food, where you could think about multispectral cameras, laser-based food sorting. I'll show a couple of examples in the agri-food domain later on. Climate and energy with smart and efficient light sources, digital infrastructure with optical fiber, optical interconnects, Wi-Fi technology, and so on and so forth. In mobility, photonics can play a role in optical sensors like LiDAR systems for autonomous vehicles, automotive lighting, for example. And in the manufacturing industry 4.0, one could think about laser welding, laser-based machining, additive and subtractive machining, as well as robotic sensors, for example. And finally, in the security and space sector, one could think about oil and gas monitoring or surveillance cameras and night vision cameras, and so on and so forth. And so let's dive a little bit deeper into what we at Flanders Make at VUB BFOT are focusing on, and well, our key focus is on free-form optical components and sensors. And basically, the idea is that if you look at optical components, you can basically classify them into either imaging optical components, which you see illustrated on this slide, and you should think there about really image-forming components, so like the optics that you put onto your camera to snap photographs, but also telescopes, AR, VR glasses, or cameras in machine vision systems or medical imaging, but also hyperspectral imaging or thermographical cameras. All these applications are imaging. But you can also think about non-imaging applications, where the goal is not to form an image of reality, but rather to focus an as large amount as possible of energy onto a single spot, like in a solar concentrator, or to distribute light according to a predefined pattern, like street lighting or automotive lamps, or in laser-based machining processes. You could think about beam shaping if you want to step away from a standard Gaussian intensity distribution and you want to reach a top hat uniform intensity distribution. This is also a non-imaging application. Others are laser scanning, LiDAR that I mentioned before, and so on and so forth. So these are the two big categories of optical components. And what is special about freeform optics is that you actually step away from the rotational symmetry that a standard or a traditional optical component has. And if you give this rotationally symmetric a spherical surface, then you will see that you have a lot of aberrations, so imperfections in the image formation of the lens, which you can solve to a large extent if you move from a spherical to an aspherical profile. But a real freeform component goes one step further and steps away from the rotational symmetry. So you can really go to non-rotationally symmetric components, which can have a very complex shape, which in turn enables unprecedented functionality while minimizing the size and the volume and the weight of your optical system, which can be beneficial in a wide variety of these applications, as optical systems need to become always smaller and smaller. At our core lab, we have tried to set up really a supply chain going from the modeling and design of these freeform optical systems down to prototyping, metrology, and proof of concept demonstration. So we really try to go from end to end, from the design to the effective proof of concept demonstration of these type of freeform components. Now here you see another view of our pilot line that we have in place. So we start from a design task where we go for a first-time right design for manufacturing, so meaning that we keep the actual making or the manufacturing of the component in the back of our minds at the time of the design, after which we can go for a prototyping phase through various schemes. So we can either go for one or two prototype components, or we can go for a small series production where we would rather go for the manufacturing of an optical mold, which is then used in a subsequent replication process to ultimately end up with either a polymer or a glass copy of your component that you want to manufacture. And of course, in all of these intermediate steps, metrology is a key aspect, because you need to check whether what you have made is actually what you want to make, or what you have made corresponds to what you have designed. So there's this feedback loop from the metrology to all these intermediate steps in between before you come to a proof of concept demonstration. Now let's go into a couple of applications to make it more understandable or more feasible or more clear what I mean with these different applications. So it can be very broad, as I mentioned before. So a couple of examples of companies that have been supported. For example, Gamma Impianti on the left here is basically a train pumping sewage system, which you would not associate with photonics in the beginning. But you can think about optical techniques to eliminate the pathogens on, for example, the seat of the toilets. And so UV illumination can be used in that instance. Photonics is a Dutch-based company which makes integrated laser beam combiners. So here, efficient coupling interfaces between free space and these photonic integrated circuits is of key importance. Heartfelt Technologies is an example of a medical monitoring device. So basically, the component that you see here in the bottom does a 3D LED-based cardiovascular monitoring to, in the end, do an early detection of heart failure. Optorobotics is a company that makes cell sorters, and here again, a light shaping application is being used by choosing an intelligent optical system to get the light distribution of choice at your target plane. On Laser is again a completely different example. So it's a Spanish company which does laser marking of corks. So again, here you see that the inscription on the cork is being done by means of a laser. So a laser scanning system to do this marking. Important is that we try to reach out as much as possible to non-photonics companies. So companies that in their essence have nothing to do with photonics, but where photonics can play a big role in their innovation. For example, Balamis, so it's a company that works on the microwave remote sensors based in Spain, which are making use of drones to do remote sensing in order to do soil monitoring and fire prevention, for example. Another example is ABC Harden. It's a Belgian company, and they want to actually make a kind of a virtual fireplace. So in this case, we've done together with them a feasibility study to make such a holographic fireplace. Or Laser, which is a company that makes cycling helmets, where a visor-mounted display was being developed. A few more examples. So in the domain of the agri-food, one can think about using a photonic sensor to do a spectroscopic analysis of, for example, strawberries to determine whether they are ripe or not for being collected. So you see here on the right of the slide that these strawberries, in terms of ripeness, can be classified into different categories. And by a spectroscopic detection technique, you can actually do this classification and decide whether the strawberry can be plucked or not yet. Laser-assisted industrial food sorting, and I mentioned it before. So you have this conveyor belt with all these vegetables coming by. So you can basically use an optical engine here to scan left to right on this conveyor belt as these vegetables come by, and you can decide whether it's an actual vegetable or whether it's a foreign particle like a stone or a frog or whatever should not be in there, and you can then blow that out of the stream to eliminate that from the collected vegetables. Another example, the inspection of sealing of food packages. So with DVC, we've been working on absorption spectroscopy of cheese packages. And so here you see the packages of cheese passing by, and again, the absorption spectroscopy system will determine whether the sealing is done correctly or not, and if not, it will be eliminated from the bunch and be sent to the waste. Turf Europe is another example where the idea is to develop a 5-channel multispectral camera for turf grass monitoring. So the idea is that you put a camera on the top of the stadium here, and that you can visualize the entire pitch in one single image. So you see you need a very large field of view. And the ultimate idea is then to see where you have regions of the pitch where you need to apply more water in order to get a uniform, high quality grass field. In this case, you see here on the right how this kind of prototype was developed. So you have different vision systems. In the center, you have a thermal camera with a large optic in the center, and then around that we have other cameras which address a different part of the spectrum. So part in the visible, part in the infrared. A similar example of a multi-channel imaging system is this one here, which was developed together with the imaging source in Germany. So in this case, you basically were targeting a passive distance estimation device. So you actually have at the same time 6 different views of your field of view of the object or the environment that you're monitoring. And again, we made here, we designed an optical system to be as compact as possible to get these 6 channels on one single CCD camera, and dependent on which images are in focus, you can actually get an estimation of the distance to that particular object. Something completely different in the weaving industry. Optical sensors can be used to detect when the yarn arrives at the other side of the weaving loom. And of course, here the goal would also be to detect as much different yarns as possible with different thicknesses, different colors, in a very compact space. So your optical detector system needs to be very compact, where freeform optics again can play an added value. LiDAR was mentioned before as well as a kind of technology to estimate or to visualize your surrounding and estimate distances, which is especially important for autonomous vehicles in particular. While, of course, there's a lot of work that is being done on solid-state LiDAR systems where photonic integrated circuits are developed to get a kind of LiDAR engine in place. But of course, once the light gets off the chip, you need to have your freeform optical components to get the light distributed to the environment in a correct way and to capture as much of the reflected light as possible. So you see here in the center an example of a 3-lobe lens with a 3-segment mirror on the right, which is being used as a free space system in combination with such a photonic integrated circuit. All right, so these were a couple of examples where photonics can play an added value in many different application domains. And we've, over the past decade, also tried to set up platforms to boost photonics innovation from the regional level up to the European level. And to that end, we have set up the Pan-European Digital Innovation Hub, which is called Photon Hub Europe, so the Digital Innovation Hub on photonics. And again, as you can see on the right, the idea is to have your photonics core in the center, but to address these different application domains in which photonics can play a role and can be very important for driving innovation. Now, how do we want to support companies with such a photonics innovation hub? Overall, if you look at the maturity over time, you will see that you start with an idea and then want to go to a feasibility study, then you go into prototyping, upscaling, manufacturing, and then ultimately commercial diffusion. So what you see in the red dots is the technology readiness level, as it is called. So basically, a company may require support on the technological side. So you orienteer them, meaning that you bring them in touch with the key experts in the field. And we can support them also with deep technology support for feasibility studies or even upscaling. But a company might also require business or financial support. So to that end, we also provide some business coaching or investment coaching when the company is being trained to pitch for venture capital funds, for example, to raise money. And finally, we also provide training and reskilling within the Photon Hub Europe project. And so here you see a bit of an overview of what I just said. From orienteering, training and reskilling to deep innovation support, and then business and investment coaching, as well as regional support is being provided in this 19 million euro EU project. The way we work is basically a 3-step action plan. So we first try to do outreach to companies from various industry sectors. For example, the Tech at Lunch webinar of today, where we try to make clear what photonics is and what innovation can be achieved by making use of photonics. And then we go, if there is a potential match, we go into a technology scouting and a business scouting, which happen at the same time, and ultimately see whether we can come to the definition of a feasibility project, which can then lead to a deep innovation support project. And after the project, we also, very importantly, monitor the customer satisfaction, and we try to measure the impact of the project, because that is, of course, one of the KPIs that we have to deliver to the European Commission, which is funding the project. And so on the right side here, you see what is the added value of this process. So for the company, it's really increased awareness of the opportunity of innovation with photonics. Can be early coaching to get in touch with key experts in the fields, which can bring important feedback and ideas to the company, and down all the way to this deep innovation support, as I mentioned before. And so here you see another overview of it, and we first do orienteering. We assign an expert, which goes and talks to the company. If there's a match, we do a project proposal, which is then evaluated by a project evaluation team within the project. Every 2 months, these things can take place, and then we can go and start with the project. So just some numbers here. Typically, the duration of such a feasibility study is 6 to 9 months. We do typically a TRL advancements of 1 to 2. And there is various amounts of funding available for this type of support, both for SMEs as for larger scale companies. But I won't go into the details. If you're interested, feel free to get in touch with me. So if you want to join one of these many companies that over the past 10 years have been supported by Photonics and Photon Hub Europe, don't hesitate to get in touch with us. As mentioned, we also do training and reskilling. So if you're interested in optics and freeform optics, we have a 3 days hands-on experience center training. Next edition will be in October of this year, but we hold this type of trainings twice a year. And we also do 1-day demo centers to, dive a little bit deeper in the enabling role of photonics in a particular application domain. So one of the demo centers that we also organize in this year is a demo center on photonics in agrifood. If you're regional and you don't necessarily need support from this pan-European innovation hub, we also recently partnered up with the Flanders Make in the European Digital Innovation Hub called Digitalis. And so basically aiming at digitization, digital technologies, Industry 4.0. And basically, this project also provides the same kind of services to some extent. So it does before invest, skills and training, financial services, ecosystem and networking, as well as business model innovation. So there's also means or possibilities to get this kind of support from the regional level by making use of the Digitalis project. So to conclude, if you're a company that sees some potential in innovating with photonics, and especially if you're a non-photonics company, I think the added value could be very large. Don't hesitate to get in touch. We have all the mechanisms in place to provide you with the support. And I mentioned specifically Photon Hub Europe as a pan-European digital innovation hub, but also the local initiative Digitalis, which has recently been started, can be used. So you have my contact information over here. And that brings me to the end of my talk. So I'll now go to the Q&A session, and I'll give the floor to Seppe Ooyen for this Q&A session.
Okay, thank you, Jurgen, for the clear explanation and the nice presentation. So far, there are no questions yet, so I suggest we wait 1 more minute to see if there are more questions coming up, and otherwise we can close the session, but let's see if there are more questions coming up.
Okay.
There are some questions. First question, could you elaborate more on applications with 3D printing?
Yes, so in principle, what is typically used in a laser-based additive manufacturing process is you use typically a fiber laser, which normally has a Gaussian intensity profile and a circular footprint. Yeah? So if you want to step away from this traditional Gaussian intensity profile and circular footprint, but you would rather want to go towards square or rectangular footprints or light distributions and have a uniform light intensity across the entire spot rather than this Gaussian intensity profile with the highest energy in the middle and an energy drop off towards the edges. You could think of inserting an optical system which can be dynamic. So you could either insert or remove the optics from your optical chain, let's say, or your optical train within your additive manufacturing machine, or by moving optics along the optical path, you can tune the size of your spot, and so you can add additional parameters to your 3D printer and not only have the laser power and the scanning speed, but also like the laser spot size, footprint, and maybe intensity distribution as additional parameters.
Okay. Then there's not really a question, but a practical one. There was someone who was having troubles entering the session, and he's asking for a recording. So, for the good understanding, we are recording this session, and everyone who has been registered to the webinar will receive the recording. So, don't worry about that. So you can watch it later again. And then to conclude, Jeffrey says he has no question, but he wants to thank you for the clear presentation and hope to see you soon. So to conclude, I give the word back to Jürgen to close the session.
All right.
Sorry. Just as I said, then there was
no worries.
Question, so I suggest we have a little bit more time. So I suggest we just deal with that one question and then close it.
Sure.
Oh no, sorry, it's not really a question. Here, does the Photonics Hub include also the link from vision system into AI models?
To some extent, this is not something we would take up personally in our core lab, but there is definitely more and more links in all activities, let's say, with AI models, machine learning, and so on. So there is definitely this link, and this can certainly be explored further if you're interested into the details there. So it's not only focusing on the photonics part as such. It's really also the interplay with electronics or with software analysis is definitely also there. Yes.
Okay, so that was it. Jürgen, you can close the session.
All right, thank you very much for attending this Tech at Lunch webinar. So I hope that I was able to convince you that photonics could play a key role for innovation. And if you are a company that is not directly involved with photonics, but you think that what I've presented today may be of value for your activities, do not hesitate to get in touch, and we'll be able to support you through the various mechanisms that are in place for additional funding, for example. Thank you very much for your attention, and hope to see you soon.